Hello everyone, and welcome to the wonderful world of Cal 2. In this video, we're going to examine the substitution method. Whenever a function you are asked to antidifferentiate does not fit any of the exact forms that we've listed in previous videos, you will need to apply certain techniques in order to solve them. Basic algebra might be your first course of action. Either through expansion, long division, or the use of trig identities, you may be able to solve the antiderivatives. However, in cases where such methods fail, substitution should always be the first approach that you use as an attempt to solve the integral. The substitution method will require that you replace an element or a group of elements in the integrand by a new variable called u. This could also be w, could be y, could be z. It's up to you, the variable's name that you wish to choose. The educated guesses when it comes to picking who will play the role of u are inner functions that you might see within the integral, functions whose derivatives are also appearing in the integral, and possibly your last attempt would be to just try the denominator if there is one. For instance, in the integral that's presented right now, sine of x plus 4 happens to be an inner function. It's contained in the power 3. Its derivative, sine x plus 4 prime, happens to be cos of x. So there are two good reasons to pick sine of x plus 4 as your u in this case. In this integral, 5x plus 7 is the inner function of the square root. Its derivative would be 5, which doesn't appear explicitly in the integral, so we may have to do adjustments later on, but certainly being an inner function should be a good cause to pick 5x plus 7 as the u. In this example, 1 minus x squared is an inner function, and its derivative is minus 2x, which is nowhere to be seen in the integral itself. Although it is an inner function, a better choice appears when we consider that arcsine of x has 1 over root of 1 minus x squared as its derivative, which happens to be the other term appearing. Finally, 4x plus 5 here at the numerator is not an inner function, and its derivative is 4, which is not clearly appearing right now. 2x minus 1, however, is an inner function, probably the better of the two choices. You notice that I've been using the word probably. Every time you make a selection for u, for the substitution, there is a bit of a leap of faith. You'll only know at the next step whether the substitution will be successful or not. So all we're doing here is making educated guesses. Once you've chosen the elements that you wish to consider as u, you're also going to have to find appropriate replacements for the integration element dx. In other words, you cannot convert the functions of x into functions of u without also converting dx into du somehow. Now in Cal 1, some of you might have talked about differentials or linear estimators, and you may have seen that du and dx are always related through the relationship du equals u prime times dx. Although it's not super appropriate, you could also think of this as du over dx is another way of saying the derivative of u with respect to x, and you would cross multiply the dx. So whichever way you want to see it, this relationship is going to be important because it is the link between the du and the dx elements. For example, in the integral sine of x plus 4 cubed cos of x dx, we've highlighted in red the choice we're making for u. U is sine of x plus 4. According to the relationship between du's and dx's, the du term is obtained from u by multiplying u prime of x by dx. Well, u prime, in this case, would be cos of x. So du is cos of x dx. Do you notice that cos of x dx already appears in the integral. That is a good sign that your substitution will be successful. You have a replacement for u, you have an expression that you're going to replace by u, and you also have what it takes to generate the du. If u were to stand for 5x plus 7 in this second integral, then du is the result of u prime times dx, so 5 dx. This time, 5 dx is not completely fulfilled in the integral. We have 3 dx, and that means potential adjustments will have to be made. If we pick arcsine of x as u in this third integral, du is obtained by differentiating u and multiplying with dx. So du is 1 over root of 1 minus x squared dx, which is in the integral. And again, a pretty good sign that the substitution will work out. Finally, if u is chosen to be the inner function 2x minus 1, then du would have to be 2 dx. Once again, we have a dx in the integral. We don't have a 2 dx, so that may mean a little bit of algebraic manipulations. Once you've chosen your u and figured out what du has to be, then you fall onto the step of identifying the corresponding u integral. In other words, you're going to have to rewrite the original integral that was dependent on x into a new integral that is only dependent on u. This will require that you make some adjustments so that all u and du terms fit adequately. You cannot leave any x terms behind. For instance, sine of x plus 4 to the power 3, we've already said sine x plus 4 is a good choice for u. Du would have to be cos of x dx to fit accordingly. And now in the integral, we actually can see the role that each of these elements plays. U will take the place of sine x plus 4. Du will take the place of the entire cos of x dx combination. And just remember that the power 3 acts on sine x plus 4, so it acts on u cubed du. This is a basic form now. It's just a power rule. And you see in practice how the substitution makes your integration easier. In the example where 3 is divided by root of 5x plus 7, we've made the choice of letting u replace 5x plus 7, and that would mean du has to be 5 dx. There is no 5 dx. There's just a dx, or a 3 dx. And that will require that we cheat a little bit. I'm going to multiply by 5 the dx that appears in the integral and compensate by multiplying by 1/5 outside, or by dividing by 5. The 3 appearing at the numerator is a constant multiple and can be withdrawn from the integral. And now we're set. 5x plus 7 is our placeholder for u. 5 dx is the exact correspondence to 1 du, and then the name changing can take place. This is also a power rule, slightly harder to see, but it is a root, so u to the half at the bottom. Therefore, this is solvable. When selecting u equals arcsine of x, and accordingly du is 1 over root of 1 minus x squared dx, the integral that we are starting off with has all of the necessary ingredients to satisfy this substitution. In fact, the u is already there and appearing as the arcsine of x, and 1 over the root of 1 minus x squared, which I've simply shifted aside to make it look like a better fit to the du, is right there and waiting. So arcsine disappears into u, 1 over the root dx disappears into du. This becomes a very straightforward integral. In this last example, 4x plus 5 over the root of 2x minus 1. We've made the choice to replace u by 2x minus 1. Let's call it a leap of faith. Du has to fit with 2 dx, or du is equal to 2 dx. Once more, there is no 2 with the dx in the original integral. So we'll create one by multiplying by 2 inside and divide by 2 outside. At the numerator, we have 4x, which is 2 times 2x. The reason why I'm going through this process is that although 2x minus 1 fits with u, it's the choice we've made to be the u, and although 2 dx corresponds to the du we're trying to accomplish, we have x's left behind. So notice how at the numerator, 2x would be unchanged, right? We'd have u's and x's in the same integral, which we want to avoid doing. If ever there are leftover x's, you can go back to the substitution, isolate x, or in this case, I've isolated 2x, and just recognize that that one term called 2x is still equivalent to u plus 1. So in the integral, I will replace every x that's left, or in this case, every 2x that's left, by u plus 1. So 2 times u plus 1 plus 5. And then, although this is not a basic rule, perhaps there are strategies we can use later. So at this stage, the u integral is hopefully one that you can solve, either because it's a basic form, or you can use other strategies to solve it. You will find the antiderivative, and only once you've found the antiderivative will you go back to the original variable x. So for instance, we said here that after applying our substitution, the integral becomes u cubed du. The power rule converts it into a quarter u to the 4 plus c. Now that the antiderivative is done, we can go back to what u stands for, which is sine x plus 4. We've set up an integral already in this case where 5x plus 7 was replaced by u. The u integral we're confronted with is a power rule that we can rewrite as u to the minus half. This is a basic antiderivative where we use the power rule. And once we've antidifferentiated, we can rewrite u. Same goes for sine. The transformation that our substitution produces converts the integral into u du, which is a power, 1/2 u squared plus c. Only once the antiderivative is found do we go back to u being equal to arc sine of x. So always the same process. Do your replacements, perform your substitutions, solve the u integral, then go back to x. And same for this last example, which required adjustments not only for the du, but also for the leftover x's. But nonetheless, we had powers of u. Here I've used expansion at the numerator, and I've divided the denominator, the fraction, term by term. So 2u plus 7, I've divided by u to the half to convert it into 2 individual power rules. And once the antiderivative is done, we can go back to the x's. For integrals that are definite, so with bounds, you should also switch the bounds to bounds of u, and that will avoid you from having to go back to x. Here's an example we've seen before, but now I've introduced bounds. So we've already said that a good choice of u is sine x plus 4, and the corresponding du, cos of x dx, is already appearing in the integral. Now the bounds x equals 0 and 3 pi over 2 means that the u value, sine of 3 pi over 2 plus 4, would be 3 for the u integral. And u equals sine of 0 plus 4 would be the 4 lower bound when we convert to a u integral. In other words, we're switching the bounds as well. And the new bounds are those we'll apply to the antiderivative. So power rule, plug in the upper bound minus the lower bound. This is FTC again. And the end result will be minus 175 over 4. Not surprising given this function has more area